Do shortcuts really exist in the universe? A passage that lets you leap across hundreds of light years in an instant. This is a wormhole. In 1935, Einstein himself derived its mathematical model. Yet, for the rest of his life, he firmly believed it could never truly exist. Why? Because the entrance of a wormhole needs something to hold it open. Negative energy. A mysterious substance we have never observed to this day. Can you imagine it? To keep a wormhole stable enough for a human to pass through, the amount of negative energy required would be equivalent to the mass of Jupiter. But what's even stranger is, in 1992, Stephen Hawking proposed the chronology protection conjecture. He said that if a wormhole could remain stable, it could become a time machine. You take one step inside, and when you come out, it might already be the past or the future. And what would this cause? Causality would collapse completely. Every choice you make could rewrite history. So here comes the question. If wormholes truly exist, why have we never observed any trace of them in the universe? Today, let's talk about this concept that physicists both love and fear. Don't rush to deny it yet. Negative energy does exist in theory. In 1948, Dutch physicist Hendrik Casimir made a remarkable prediction. When you place two uncharged metal plates in a vacuum and bring them extremely close together, quantum field theory says the vacuum between the plates will create an attractive force. This prediction was precisely measured and confirmed by physicists in 1996. This is the famous Casimir effect. Experiments showed that in the tiny region between the plates, negative energy density indeed appears. But here's the key problem. The negative energy produced by the Casimir effect is incredibly tiny. According to calculations, between two parallel metal plates spaced 1 meter apart, the negative energy density is so small. It's almost negligible, equivalent to having just a single quantum state within every quintillion cubic meters. This means that to stabilize a wormhole large enough for a person to pass through, the negative energy density required would be unimaginably higher than this. But theoretical physicists haven't given up. In 1988, physicists Michael Morris and Kip Thorne designed a revolutionary wormhole model, the Morris-Thorne wormhole. This wormhole has none of the deadly event horizons found in black holes nor the singularities that would tear you apart. Its mathematical model shows that with enough exotic negative energy matter, a wormhole could form a smooth tunnel through space-time. What's even more fascinating is that a wormhole would bend light like a lens, allowing you to look through it and see the cosmic landscape on the other side. But theory is one thing, reality is another. The mainstream view is that, on macroscopic scales, we simply cannot produce enough negative energy to keep a wormhole stable. So could wormholes already exist naturally in the universe? Some theoretical physicists suggest that wormholes might be hidden deep within the cores of rotating black holes. When a massive black hole spins at high speed, its internal structure undergoes astonishing changes. The central singularity becomes a ring-shaped structure, which could theoretically connect to another region of spacetime. But the latest research from 2025 offers a sobering conclusion. Numerical simulations show that such wormhole structures are extremely unstable. When normal matter enters, it triggers gravitational collapse, and the wormhole snaps shut instantly. And when exotic matter with repulsive properties enters, the wormhole violently explodes, ultimately splitting into two separate space-time regions. In other words, even if wormholes naturally exist, crossing it safely would still be almost impossible. So then, can we create a wormhole in the laboratory? In 2022, a highly controversial experiment appeared. Scientists at Google used a quantum computer to simulate certain features of a holographic wormhole within a microscopic system of 9 qubits. They constructed a special quantum model that allowed quantum information to be input from one side and emerge from the other with dynamical behavior, matching predictions from some wormhole theories. The study made the cover of Nature, and some media called it the first wormhole in history. But it's important to emphasize that this claim sparked intense debate in the physics community. Many scientists pointed out clearly that this was merely a highly simplified quantum simulation. What it simulated was a so-called holographic wormhole, a mathematical object based on a specific theoretical framework, fundamentally different from real gravity-generated wormholes in our universe. This experiment does not prove that real wormholes can exist, nor can it be used for interstellar travel. Its real value lies in providing an experimental platform for exploring possible deep connections between quantum information and gravitational theory. Returning to the essential question, if one day a wormhole appeared before you, what would happen if you tried to cross it? First comes the challenge of tidal forces. The curvature of spacetime in the throat of a wormhole is enormous. Your head and your feet would experience gravitational pulls of different strengths. If the wormhole is too small, that force would tear you apart down to atoms. Even if you're lucky enough to enter the wormhole, the journey through it is full of unknowns. According to general relativity, time may flow at completely different rates. At the two ends of a wormhole, you might feel only a few seconds pass, but when you emerge from the other side, the outside world could have aged thousands of years. Or you might return to the past, triggering mind-bending time paradoxes. The wildest shortcut in the universe still exists only in theory and imagination. The equations of general relativity allow it to exist, but it requires negative energy matter to remain stable. Quantum mechanics tells us that negative energy does exist, but only in tiny, tiny amounts, far from enough to support a macroscopic wormhole. We still haven't observed any direct evidence of wormholes in the universe. Perhaps the answer lies within the quantum gravity theory that we have yet to fully construct. Maybe one day, when we truly understand how quantum mechanics and general relativity unite, when we master the ability to manipulate the fabric of space-time, we will be able to open a doorway into the depths of the universe. At that moment, interstellar travel will no longer be science fiction, but reality. Until that day arrives, wormholes remain the most beautiful equations in the notebooks of physicists, and humanity's most distant dream of exploring the cosmos.